What's going on, everybody? This is Mr. Diamond, and we're going to be going through the notes / the examples for projectile motion. Now, after looking, I just feel like it's going to be so much easier if I just kind of go through all of it in one movement, not really worry about the actual PowerPoint, and just kind of discuss it while I'm working out examples. So in the last chapter, we focused on 1D kinematics, and things were either moving vertically or horizontally, but in real life, most objects will have both types of motions. So we would call them 2D kinematic instead of 1D kinematic. So they've got 2 dimensions versus 1 dimension. For most of these projectile problems, we'll be ignoring wind. There's a couple of them where wind is part of the thing that we're actually considering, but we're usually going to ignore drag and stuff like that. Often what will happen is you'll have an object that's moving through, for example, if you have like a cannon that's being fired. So I'm going to draw me a really crappy cannon here. I'm going to put it on stands because you can't just have a cannon sitting on the ground. That would be unreasonable. Then we'll have a little fuse. So if you've got your cannon and it's, let's say it's up on like a hill, and you fire that cannon is imparting a horizontal velocity to that cannonball. It's imparting to it a horizontal velocity vector to that cannonball. And that velocity is going to be constant. So whatever this is most likely going to be, at least in the x direction, constant. That's usually. But then there's also going to be a y component, and that y component is affected by gravity. Gravity is the thing that's pulling these things back down to the ground. For basically every problem, gravity is your determining factor for how long something is going to stay in the air. The easiest way, as when we usually do these things, is to just start working on our problem and kind of talk it through. So we're going to start with an example of a base jumper, and I'm gonna move it down a little bit so we've got a little bit more space. A base jumper is just going to run off of a cliff. I'm sure a lot of you guys can kind of relate to that feeling right about now. So we've got a cliff. If the cliff is a 65-meter tall cliff, and they are running off, kind of like they're dancing more than running, but they run off the cliff with a v in the x direction initially of 8.0 meters per second. How far in the x direction do they go? So that's our question here. How far away from the cliff will they land? Now, we're also going to assume that this person has not been living through 2020 and is not actually like miserable and just jumping off it. We're going to assume that there's water down here. They're going to land at water that's 65 meters below. So the arc of the movement that this person is going to take, their actual velocity, is not just going to be a straight line, because this horizontal velocity should stay constant. They left with that velocity. There's nothing impacting it. We're ignoring wind resistance and anything like that. In their y direction, they're starting with nothing, but they're going to be pulled down by gravity. So as they go, you're going to expect them to get pulled further and further and further down until they land here. So notice, this is not a straight line. This is not going to be a triangle we're going to make out of this one. This is a curve that's going to be going on here. So as with before, I like listing out everything that we've got, but now we're going to have an x column and we're going to have a y column of information, just like we did with our relative velocity examples. So we'll start with our v naught and our v. We'll have an acceleration, we'll have a time, we'll have an x, we'll have an x naught, and we'll have an x. So that's all of the variables that we've ever really cared about. And then we'll have the same thing here. We'll have a v naught, and we'll have a v, we'll have an a, we'll have a t, we'll have an, this time will be a y naught, and we'll have a y. Now let's just figure out everything that we have from both of these pieces of the problem. Let me go back to my camera and make sure you guys can see this okay. Okay, good. Initial velocity in the x direction. We've got 8.0 meters per second. And they're also going to end with that as their x velocity because there is no acceleration. So that's pretty easy. For y velocities, they have no initial y velocity. We don't know what their final velocity is going to be, though. So this is currently unknown because we know that there's going to be a negative 9.8 meters per second squared acceleration in the y direction because of gravity. We know our y position starts at 0, and then we're going to fall 65 meters. So that's negative 65 meters. And the x direction, our initial point is 0 meters, and then our final x is actually what we're looking for. This is the key piece of information for the question. That's what we're going to be trying to figure out. So looking at this information, there's kind of a glaring problem you're going to notice in the x direction is that all of the equations we had last chapter, which if I pull up, and these all hold true, all of these equations require something that we don't have. We either need time, this one needs time, this one needs time, this one needs time, or we need to know our x distance. This one doesn't involve time, but we need to know our x. So we actually can't do anything in our x direction, but we can solve for t, because remember, time is going to link x and y directions. Time is going to be the same. Whatever time he spends moving horizontally is the same amount of time he's going to spend going vertically. So now if we actually check our y direction, we've got a v naught, we have a y naught, we have a final, we have an acceleration, and we don't have a time. We can solve using this equation here to find time. And if we know time in here, we'll know time over here. We'll know our time in the x direction as well. We can use that to solve for our x. So our step 1 here is going to be use the y direction to find time. And just like I said up here, or whenever I was talking about it earlier, the y direction and gravity especially is usually the limiting factor for how long something stays in the air. And since we're looking for time, it makes sense we'd use the thing that's how long something is happening. So I've got all my information up here. We're going to in this case, is going to be y equals y naught plus v naught y t plus 1/2 ay t squared. I'm just doing these. You don't have to do these little subscripts here. I'm only doing that because I want to make sure that we're very thorough and we don't accidentally use one of our x variables up here. You won't have to do that on tests or anything like that. If you feel confident that you can do it without it, you don't have to. So let's go ahead and plug in anything that we can cancel out. Our v naught is 0, so we can get rid of that. Our y naught is also 0. So it looks like our final pieces that are left are negative 65 equals 1/2 negative 9.8 t squared. Solving that, we'll get t equals the square root of negative 65 over 1/2 times negative 9.8. And our t is going to equal, pull out the trusty calculator, square root negative 65 over 0.5 times negative 9.8. We'll get a time of 3.6421567995 seconds. Obviously, we're not going to use that full one. The question that I gave you, we only had 2 sig figs, so we'll just call that 3.6. Now, you're going to probably just plug in this whole number in your one, but for the purposes of writing it up here, I'm going to write 3.6 seconds. 3.6 seconds. Because again, this is the only piece that we can use that always will cross over. Time in the x direction has to be the same amount as time as the y direction. So step 2 is use time to solve for x. So now looking at all the information that we have here, if we're trying to find an x, In my opinion, we don't need to use our acceleration. It's 0 here. So we can actually just use v, or where is it at? We can actually use v equals x, delta x over delta t. That's going to be kind of the easiest one to use right there. So our velocity that we're traveling is equal to the change in x distance over the change in time. Rearrange that around, and we will get our change in x, our displacement, is equal to v delta t. So our change is going to be our 8.0 times our 3.64. Now again, I'm just going to carry over the full number because this equation is easy enough to keep that number intact. So I'm going to do times 8, and I got 29.137 meters away, which, if we go to sig figs, would be 29 meters, because the only thing is I have 2 sig figs. And then we'll box that. So that is our answer to this question. It'll be, if you run off of this cliff that's 65 meters high at a speed of 8 meters a second, you should land 29 meters away, assuming that there is no other forces or factors at play there. Now I'm going to ask a second question. So second question, I don't know why I did question mark 2. What speed are they hitting the water at? So what we're going to have to do in this case is we're going to have to actually find our velocity vectors, both the vertical, or the going downwards, and the horizontal, going to the right. Combine that together to get a total speed. Now it says speed, very clearly says speed, so we don't actually need an angle. We just need to know what the speed value would be from this one. So let me scooch this over a little so you can see a little bit better and get the rest of it. So we need to know, well, we know our V final, so I'm going to do V1 just to make sure it's clear. Our V1 in the x direction is the same thing as our V naught because it has the same constant speed. So it's going to be 8.0. But now we're going to have to solve, you notice I left that question mark there. We're going to look for what that V is going to be. So our V in the x direction, we've got all of our other pieces of information. The easiest one is probably going to be V in the y direction is equal to V naught in the y direction plus A in the y direction times time. This piece comes to 0, so it's just going to be negative 9.8 times our 3.6421 number. So I'm actually going to back up on my calculator, get that number whole cloth again, times negative 9.8, and I get that their downward velocity, remember that's why it's negative, their downward velocity is negative 35.693. Again, that's meters a second. And then now we're going to go ahead and say, okay, well, our horizontal vector is 8.0, and our vertical vector is 35.693. That means our total vector must be this right here. Our V total, and I'm using V even though it's technically speed just because that's kind of how we've gotten used to it at this point, is going to be the square root 8.0 squared plus 35.693 squared. So let's go ahead and plug these bad boys in. I'm going to square that number so I don't actually have to do any other weirdness there. And that's interesting. Comes out a whole number. Probably either makes you feel like you've done something horribly wrong or that you've done something correctly. In this case, it's actually a sign you've done something correctly. 1274 squared. Square root of that. Oh, not squared. My bad. 1274. Don't need to square it. So we get a total value of 36.57868, or if we round that, they're going to hit the water with a speed of 36 or rounded up 37 meters a second. Now, again, it asked for speed, so we didn't actually need to find this angle, but if we did, I'm confident that you would feel good at doing that because we've done that a whole bunch of times already this chapter. Anyway, that is our projectile motion example. If you guys have any questions, please let me know. Otherwise, I hope you have a great rest of your day. This is Mr. Diamond signing off. Hope to see you guys soon.